All right, everybody, I think we're going to get started again. Sorry to interrupt your conversations, but we're going to stay on track here. Up next, we have a fantastic speaker, a gentleman by the name of Brian Albers from Cardinal Glennon Hospital, who's going to speak to you about 3D printing applications in the medical field. So, Brian, if you'd like to take over and wow them with your knowledge.
No promises.
All right, thanks.
First of all, welcome. Thanks for coming. As he said, my name is Brian Albers. I work at Cardinal Glennon Children's Hospital in St. Louis, Missouri. I've been working in medical 3D printing field for about 7 years now, and so we're going to kind of give you an outline of the different processes that we go through, as well as run you through a couple of cases that I have worked up. First and foremost, the boring stuff, financial disclosures. I receive no direct funding from any company. SSM Health is actually a Stratasys Center of Excellence in medical 3D printing. So we do collaborate with them on another number of projects, but I don't sell for them. So 3D printing in the hospital and a hospital setting, so we've got sort of four of the main categories that we're going to go over, and that's the segmentation and image selection. So how are we actually going to build the model off of patient-specific data? Then going into engineering partnerships, where you're going to see benefits for things like, I like to call it free labor with students, as well as the 3D printing methods, how you're going to bring your part into the real world, and then go over a couple of cases that we worked on that I think you guys will find very interesting. So within our program at the hospital, we have four major specialties that we work with. Maxillofacial plastic surgery, which deals with everything sort of from the mandible up, ranging cases like craniotomies and cranioplasties, which is like this case we have here, which is where we actually went and built in. This is a congenital defect. A child is born missing parts of their skull, and we'll go through and take a graft from another area of the skull. And in doing that, the physicians prior would just use sterile paper and a pencil to trace out and decide how big of this graft is. And from there, we can actually build a template digitally and give that to them. So not only can they plan the surgery prior to the actual surgery date, but can also give them a better understanding of where they're going and actually know exactly how much they need to take for the graft. We also work in cardiology, cardiothoracic surgery, neurosurgery, and orthopedics. So we get into the segmentation programs. This is just a very small sort of outline of some of the programs available, programs that we've used, both paid and free. Materialized Mimic Suite is one of the most common, however, one of the most expensive. They do have research programs available where they do work with universities to get the software to build the models. There's also Philips portals, which if you don't have their CT scanner, you basically can't get it. So you're looking at least $500,000 to $1 million to get access to this software. However, it's very basic in its operations, whereas Materialized Mimic Suite allows more advanced segmentations, and I'll show you some screenshots from that. There's also D2P, which stands to Dicon to Print. Jesse and Aaron won't like this, but this is actually from one of their competitors called 3D Systems. I'm okay. You're okay with it? All right. They're helping the world. Exactly. And then there's a program called Osirix. You'll notice that's actually on both sides, and this is a Mac-only program. So I have not gotten to really play with it as much, but they do have a paid version, which just has more features. However, you can get the free version on any MacBook. I believe you can download it from the store and do basic segmentation and model creation. And on the free side, you have Invicilius, which was actually a graduate student project, I believe the University of Brazil, which allows very basic segmentations, but it's one I highly recommend to people. If you do have a CT or an MR, you can go to the hospital where you've got it, request a copy of the scan, they'll burn it onto a CD, and you can load it in Invicilius and build simple assemblies of your anatomy. And then also 3D Slicer. They have a paid version as well. We use this program for merging. So you can actually pull together, merge and align a CT and an MRI for doing more complex assemblies. So breaking down for the replication of anatomy. So we build our scans, our models based primarily off MRI and CT data. Just a quick overview of those. MRI, magnetic resonance versus CT, which is blanking topography. So these are the two most common three-dimensional scans. A CT is similar to what you might see on an X-ray. There's radiation involved, so we tend to shy towards the MRI in a lot of our patients because we're dealing with a pediatric, and they're a lot more susceptible to the radiation. When you're building these scans, you need to also make sure you have that right resolution. So we're talking sub 1 millimeter slice thickness. So if you're not familiar, a CT scan is essentially taking the part of the anatomy and then taking slices of it and then stacking them on top of each other to get the scan. So you need to make sure that you have these slices that are small enough. Otherwise, your model ends up looking like it was built out of Legos. And there's also the appropriate scan sequence. You get this more in MR. There's T1 and T2, which is just different phases of the hydrogen molecules when it takes the actual picture. And those allow you to isolate different structures in different phases and allow them to have what's called structure differentiation. And that's where you kind of get into highlighting what you need to see and what you want to segment. You want to have a nice clear line on the anatomy in order to make sure that you're getting the most accurate and well-defined model. Here you can see, and this is actually an MR. So you can see actually the blood pool here, the right ventricle left, right ventricle left. Wow.
There's all three ventricles in one atrium.
Yeah, sorry. This was actually I believe this case was a congenital abnormality where there was fusion. But yeah, I'll have to fix that. Thank you. But you can see here the use of contrast material, which is can be a radiopaque material and allows the differentiation of structure. So as the blood's flowing through the heart, it shines up nice and bright, allowing us to easily pull out the structure. So the segmentation process is very simple. You're basically highlighting what you want to see. And so you're going through, and on this particular case, which is actually my own CT scan, you can see here that we've gone through and highlighted, and it's a color by numbers. You're highlighting in blue the skull, the cranium, the maxilla, and then in yellow, we're actually highlighting mandible. And through this program that we use, which is the Materialize Suite, where we can build off multiple masks and build a more complex assembly, which allows us to print. We have the ability to print complex assemblies, which means we can import more than one model and then print them together, be it fused or not fused, as well as simulate different materials in between them to, for instance, articulate a spine. And so we can build these assemblies. And you see here, so this is a thoracic scan. You can see this is the heart, this is the lung, yellow here is the airway. So we actually go through and you break them into different masks is what they're called. And each one of those masks will create its own independent STL file. And through the program, we actually conserve all of the coordinates, which means that when we then import this into, for instance, GrabCAD print, all of the coordinates are preserved. And so the parts come through as a complete assembly, which means that all of the relationships between the structures are preserved, which means we can build these models in one single pass, which means there's no minimal post-processing, no assembly, no gluing. Sorry, not to show off. The models to run them through and actually create them a lot more accurately for these physicians who are going to be doing trial procedures, taking measurements and gathering data from before they treat the, while they plan to treat the patient. And then you go into actually exporting into the CAD programs, which I'll outline in a moment. But that's where you can go through and actually make manipulations. So if you want to build something like a surgical guide or a splint, you can go through and using these programs, you can, for instance, on my original, the earlier picture, building those cranioplasty plates is we can go through, analyze the contours of the skull. And from that, build a surgical guide that will allow the physician that when they're going through to take the graft to see the appropriate curvature, know where they're going to take the graft from, and then have that template that they can use to trace it. Because especially when you're dealing with children, I believe my youngest patient for cranioplasty surgery was about 1.5 years old. There's not a lot where you can take a graft from, and taking too much or even taking too little can be extremely detrimental, because if you take too little, you're not properly filling the hole, or you may need to take a graft again from somewhere else, or taking too much, you still are compromising the structural integrity, albeit slightly, but you want to take as little as possible. You want that perfect fit. And then you come into model validation. So and that's something very important in doing these models, is preserving the coordinates. When you have the model, it has an XYZ coordinates. Those in engineering would be familiar with the Cartesians. And so you have to make sure the program does not default those to something like 0, 0, 0 and put it in the middle of the program. Because by preserving those coordinates, we can then take these models and then overlay them back onto the scans, which means that when we were doing something like perhaps rebuilding a structure, or if we were trying to manipulate the model in some way, add a thickness to simulate perhaps myocardium, we can go through and overlay. And it's faint on this picture, but you can see these thin lines around these structures. And that is actually the overlay. So we can go through and confirm that the changes we made, there's nothing erratic, there's no mistakes, and we can actually view it slice by slice in relationship to the patient's original scan. And so now we get into the CAD programs. They were outlined earlier, so we'll kind of go over this really quick. Materialized 3-matic is what we use, and there's an asterisk by that one because that's one of the only ones that I know that has FDA certifications and a 510K, allowing it to be used in direct patient care. There are programs like Fusion 360 and SolidWorks. They're on sort of both sides because as students and EDU email addresses, you can actually get a free copy of Fusion 360 to use as you need for non-commercial activities. SolidWorks, you still have to pay for the student license. That's why it's at the bottom of the list. They upset me with that one. In the free side, you get programs like Mesh Mixer, 3D Builder, which 3D Builder is actually embedded in Windows. It's a relatively simple program, but can allow minor manipulations and as well as positioning and prepping for 3D printing. And so when you get into these models, it's more than just replicating anatomy. So we had talked about rebuilding perhaps a heart for mapping out congenital defects and planning out surgery. But the other things you can get is, like as we spoke, surgical guides, implants, splints, and universal tool adaptation. And you can see here, this is a case that actually I'll outline a little bit more in later slides, but you have these titanium pieces, and if those are familiar with trauma reconstruction, they talk about having a titanium plate, and that's what that is right there. That is a version of it. And they come in, they're sort of universal. That's a mandible plate right there, which has this slight bend right here, and it has a curved radius there to sort of fit to a generic mandible. And the surgeons during the procedure will actually go through and pull the pieces together, lay this mandible template on there, and then they'll kind of pull it out and they'll make minor adjustments to it until it fits the anatomy properly and allows them to just screw it in place. So there's actually a lot of time sort of wasted in the operating room, while the patient is there open. And so we can actually build these models and build what we call perfect reconstructions and print them out. And so the surgeon the night before can bend these titanium plates to the structures, send them off to sterilization, and the next morning during the procedure has this template, which has been built off of what we consider, like I said, a sort of perfect rebuild. So he's spending less time with the patient open on the operating table, which means there's an exponential reduction in the risk of infection, MRSA. There's statistics studies going about how much past a certain amount of time is the likelihood of errors to occur, and also cost savings. The operating room, I believe it's about $100 per minute just for the room. That doesn't include physicians, staff, any ancillary services. So when you're talking about taking upwards of 3 hours off these procedures, that can be a big cost savings, as well as for the hospital, which means they can have an increased throughput in their operating room. And then we get into what I like, and that's where the engineering comes in, and that's what my background's in. The engineers come in and partnering with physicians because they offer new abilities in design and development. Physicians aren't necessarily trained. Actually, they are not trained at all in any kind of CAD software, any type of technologies in rapid prototyping, 3D printing, additive and subtractive manufacturing. That's not within the standard scope of practice. So by bringing in engineers, they're bringing in these new production methods, pairing up with the physicians, because engineers don't have a medical license, which means I can't just go into a hospital and start 3D printing structures. You have to partner with a physician. But at the same time, the physicians don't really know about 3D printing. They don't have access to them. Whereas every engineering school has at least one, usually upwards of 5 3D printers available to the students, because it's actually part of the curriculum these days. And so that's where we get into different variables with it. It's like communication is key. Like I was saying, the physicians are one side, the engineers are the other. They have to partner together in order to develop a process like this. And the other responsibility of the engineer is understanding the current treatment methods. When I first started at Cardinal Glennon, I didn't actually work on a full bore case for about 6 months. I spent the first 6 months there shadowing physicians, shadowing surgeries, even one-on-one meetings with patients, understanding what the physicians are doing, how how their standard is right now, what's involved, how they explain situations to the patients, how they're using currently available tools within the operating room, and sort of using my knowledge in design and development and saying, how can we improve that from an engineering standpoint? How can we make patient-specific medicine applicable in every sort of facet of a patient's treatment? As well as also having production expertise. Again, we come back, why we're all here is 3D printing. So again, if physicians don't understand all the different materials involved, they don't understand that there's different certifications, there's different benefits for things like photopolymers, which is we get on PolyJet, where you can get full color, but tend to be a little bit more fragile, versus thermoplastics, which you can get something that's a single color, but very strong. And as well as just the different properties for when it's printed on maintaining things like short-term and long-term biocompatibility. Can this become in contact with human skin, and what's its rating? Mucosal contact, which is like dental applications, and blood contact, surgical intraoperative guides, and how long? So there actually are a number of certifications. For instance, the Stratasys material that we use, not a plug, Med 610 is certified for 24 hours at contact, at blood contact. However, it does carry an infinite certification for unbroken skin, which means as long as the device is not compromised in any way, and nor is the skin compromised in any way, this model can be applied directly to a patient's skin for an indeterminate amount of time, as long as necessary, assuming the criteria are met. And there's some important notes for collaboration, and that is things like validation. We spoke about how we can overlay it on the scan, but it really comes down to the physicians. They're the ones that carry the liabilities. They're the ones with the medical license. They're the ones with, that are susceptible to lawsuits, to put a fine point on it. So they are the ones that have to be the ones that finally sign off on everything. So I can build the most beautiful model in my laboratory, but if the physician does not agree with whatever assessments I made, compromise has to be come to, but they are the ones that ultimately have the final say, especially in whether or not they even actually use it, because I don't assume the liabilities they do. I don't have a practitioner's license anymore. So that's a very important piece that you have to understand in that, is that they are the final say, and unfortunately what they say goes. They have an ego, and they like to let you know. So now we get into sort of the material applications, and we'd outline this a little bit. You get thermoplastics, which is like SLS and FDM. I know you guys are mostly familiar with FDM. SLS is becoming more and more common in sort of trickling down from production environments. And that's where you get strong functional parts. You're working with a thermoplastic, ABS, PLA, nylon. And these, like I said, they're very structural parts, but you really only get sort of one color per print. And these are for building things like splints, wrist splints, for instance. That's something actually we're working on with in orthopedics. Surgical guides, because they maintain short-term biocompatibility. Drill guides for use in dental applications. The cranioplasty surgical guides can be done on a thermoplastic. But one of the big advantages too in the medical field is long-term biocompatibility, and that's something that's potentially implantable. Currently, the only material right now is a derivative of PEKK or PEEK. There's a number of different formulas, but polyether ether ketone is the sort of base for these long-term biocompatibles for building things like a cranioplasty plate when, for instance, grafts are not available. And then you get into photopolymers, and that's on your SLA and your PolyJet. And these are the kind of prints where you can see the ability to print in multiple colors and do these complex assemblies. Like, for instance, this is actually 3D printed. It's a single run 3D print, pulled off the printer, support materials cleaned off, and that is what you get, albeit that one's slightly more polished and professionally photographed. But you have the ability to do and build the relationship, mix colors, and build this assembly, which I believe this one is 56 parts, I believe, all printed simultaneously in one model. They do carry the ability for short-term biocompatibility. Again, that's the Stratasys Med 610 material, which is 24 hours at blood contact, and then infinite for unbroken skin contact, and that's still considered a short-term because it's all classified on contacting within the mouth mucosal membrane as well as blood. But then you also have the ability for clear models. And this is one of the big things, again, this model here is building these complex structures. Model here I'll pass around. The ability to do something clear allows us to see the relationships of all of these different structures to themselves. For instance, this particular case here, which actually I'm working with ATSU Dental School, shows a mass within this patient's mandible here. And then it also shows its relationship to all of the teeth, how they're being pushed out of the way, how they're being repositioned by this tumor. And so the physicians are going to use this and assess it to decide how they're going to extract. And then from there, they can decide how they're going to reimplant the teeth, how they're going to proceed with this case. And we can print this in such a way, and as much as I hate to say it, I always tell my physicians to lie to me, is they can break this. They can drill into it. They can do a mock procedure on this. If we have set up a number of these for the more complex cases, they can actually break it, and we can do surgical simulations. So that we can print 3 or 4 of those, and we can simulate different variables like bone marrow, for instance. We don't have the new bone matrix yet. That's something we're working on, but we've found other ways to simulate it in these multi-part prints in order to allow the physicians to go through and do the procedure, and even do the procedure 6, 7 times in their office with their team before they even get into the operating room, which is incredibly important, especially when you're dealing with pediatric patients. It's, everything's closer together. Everything is a lot more, small things can go bad very quickly. So it allows the physicians to plan out and even try multiple different processes, multiple different approaches to the particular case before they get into the operating room, and really play around with the variables of which potential will work the best for that specific patient. And so this is the case. I like to present this one, and this goes in. It was with the adaptation of the universal surgical instruments. And so this is a mandible reconstruction. This patient unfortunately suffered a gunshot wound, shattering the mandible. And here it looks like it's 3 pieces, but there's actually one behind. So it was actually in 4 large pieces, and then about 15 or so other fragments. And the problem with this particular patient is due to lifestyle as well as prior traumas. Things like the dentition were missing in the back here. And that's usually what the physicians are going to use to align it. So they'll pull all the pieces together and then use your teeth, because you feel your teeth, they sort of pull your jaw into position. So we can use that to align. However, in this particular case, that wasn't an option. So what we did was actually, I was able to take the mandible, take the good side, because all the trauma was localized here on the patient's right side. So I was able to take this good side, mirror it, and then rebuild the mandible. And then from there, we were able to actually do fit and finish testing. So we can test range of motion. We can test and make sure that there's going to be no interference at the condyles and the TMJ joints, the back where your jaw pivots. Also simulate and try and have some semblance of dentition alignment. So things like eating are not going to be negatively affected. And so I was able to digitally rebuild this entire mandible, test all of these things on the computer within a few hours. And this case actually happened over 3 days, just to kind of give you an idea. And this is why we put a lot of value on bringing these within hospitals, because these cases that you don't have the time to wait to have it be printed at a service bureau. Whereas with this case, as soon as it came off the CT, I was able to get the images, get to work, and work one-on-one with the physician and their team to rebuild this. But so I was able to build this all digitally and test it. The physicians, we're still sort of bringing them up to speed. I trusted this, but they still want to see something physically and be able to test it. So we were actually able to print it out in time. And the physician went through, because a lot of them, they're still getting into 3D printing. So they still have the feel. They still understand the relationships of the structures. So we were able to print that and then allow him to run through his normal, what he would be doing in the operating room, testing range of motion, alignment, and basically build his confidence in my reconstruction. And then from there, I guess the picture you saw before, we were actually able to bend all the titanium plates that he needed to the mandible the night before the procedure. It was 12 hours before the procedure that this actually happened. We were able to bend these in the office, test the fit and finish, plan out where they were going to put the screws in relations to things like the alveolar nerve canal, which is right here in the front. We're able to see all of those structures on these models as well, so the physicians can thoroughly plan what they're going to do. And all in all, the physician, Dr. Alex Lynn, kind of said he saved about 4 to 5 hours on this procedure, which is a lot of money, but also just a lot of time saved. I mean, that could be a whole nother procedure that they could schedule that day by being able to 3D print and fit this outside of the operating room. Another one of the cases that I like to talk about, this is a case of neurofibromatosis, where one of the brain tumors coming off the cerebellum was actually eroding away at the skull. And this was actually one of the first cases I worked on at Cardinal Glennon. And you can see here, this was the defect they were going to be replacing, but unfortunately, due to the patient's condition, they decided they required a plastic plate versus doing a bone graft. And the other issue was, you can see how it's sort of highlighted around here. All of that bone, we decided based on looking at the CT, was actually being eroded. The hole was the only one that was the first to break through. So the physicians decided, oh, we're gonna actually take out a little bit more skull in order to put this plate in and have a good point for it to fixture, so this child is not going to have issues, because those of you who are kids or have kids know that they can break anything. And so we've got to make sure that if this kid goes on to play soccer, they get hit with a ball, that they're not gonna, it's not gonna cause negative, not gonna have negative impacts, as well as not having a limitation, because even if you try and put a limitation on a child, they're gonna find a way to get around that. So, and the physicians come through and they also mapped out some blood vessels and decided the area where they want to take this graft. And before they actually drew on this, I sat in an office with the chief of neurosurgery and the chief of plastic surgery, who were working together on this case, on a phone conference with a company, going over what they want to resect and where they, what the size and the shape and the fitment of this cranioplasty plate. Meeting went on for about 45 minutes of them going back and forth screen sharing, trying to purvey the information to the engineers to get this model made. And it just so happened to this was just to test the printer that I printed this case. I ran down to my office, got this model. The physicians took some Sharpies to it, drew on all of these notes that you see here, the position of blood vessels, the internal resection and the external resection. The sales rep who was in the office with us took pictures of it, sent it to the engineer. Meeting was over 10, maybe 15 minutes after that. And by the next morning, we had the approved plate. So had we utilized this technology at the beginning of the meeting, it would have been 15 minutes wasted versus hour and a half wasted with two of the most important physicians and busiest people that I actually know. And here we see, this was actually just a 3D printed demo we did on our printer to show the plate, the blue plate itself on the patient's skull. So this is outline of a couple of our publications. I'll make them available to Aaron if you want to reach out to him or myself. I can get you copies on. These are the 3 papers that we currently have published. We have about 4 more in the hopper, as well as a couple of other case studies that we have worked on actually directly with Stratasys. And here's my contact info. Please feel free to reach out if you guys have any other questions. The SSM Health is, if you guys are interested in any kind of partnerships, general consulting, the second email, Albers@gmail. I'm happy to help. I do work with a number of other, like First Robotics. I've worked on prototype development as well. Any questions?
What is your determination of when you do FDM versus polyjet?
Within our scope, we tend to go more for polyjet just because of the complexity of the models. The FDMs, they work great for making structural parts. So for instance, if we're doing like an ear recon, something that maybe doesn't require support material, has relatively smooth structures, FDM will be sufficient. But most of what we do ends up in some way or another getting sterilized. So having a solid part in itself is actually very important versus the honeycomb internal structure of the FDM. So, I mean, we've used it occasionally for prototyping. There's no denying that it's significantly cheaper than polyjet. If we need to make something small and then kind of understand the relationships before we actually build it in polyjet. But yeah, we tend to err more on the side of polyjet, just the ability to do complex assemblies, the mixture of the hard and soft materials in order for things like spine articulation, and as well as doing, like, for instance, our neurosurgery simulators. That way we can have different durometers through the model for things like blood vessels, white matter, gray matter, as well as any mass, tumor, anything that we're trying to extract in the end. Any other questions? All right. Well, thank you for having me.
Thanks, Brian.